All right, everyone. So what we're going to talk about right now is an introduction to what we call power factor correction. It's kind of what we have been leading up to with our discussions of essentially the law of conservation of power, and then also our discussions about efficiency and how we actually can derive in some notion of efficiency within a system. And if we go back and think about power factor is basically the amount of real power that we're actually delivering with respect to the amount of apparent power within the system. So basically, as that ratio gets closer and closer to 1, we have mostly real power that's actually being delivered within our system. Now, sometimes with this idea of having reactive power in the system, and maybe even too much reactive power, we actually, by the law of conservation of power, can actually introduce the opposite reactive power within the system by adding elements that may actually bring that power factor closer and closer and closer to a value of 1, or basically being essentially 100% truly basically real power within that system. Is everything truly real power? Well, if we think about basically the negation of effect of positive reactive power and negative reactive power within the system, then we can actually at least design a system that would deliver a mostly efficient basically power transfer. Now, if we think about basically, it was weird, my phone just went off. So if you just heard that ding, that was everything that's connected to my system. So if we think of essentially what is a normal system that we see within society, basically resistive inductive in nature. And if we think about that in terms of power transmission, power generation, and even power supply to factories, then most of the time what we're going to see is mostly inductance within that system itself, especially if we think of basically motors that are working within a factory on the assembly line, or if we think about the amount of inductance that's actually on the transmission line itself when we utilize transformers to step up and step down the voltage. We're going, by default of use of an AC system, an alternating current within our means for generating that power, we're going to see inductance on that line. And sometimes we may get too much inductance on that line. And essentially, as we raise basically that reactive power, then we actually increase the amount of apparent power, or essentially what is basically the amplitude of the instantaneous power that's actually being generated. So if we actually want to get rid of some of that reactive power, we can actually introduce, in this case with mostly positive reactive power, we can introduce negative reactive power within that system that's actually going to cause that apparent power, that hypotenuse of the apparent power, to actually lower closer and closer and closer down towards the real axis. So obviously, once again, if we think of having mostly inductance on that line, or inductive reactive power essentially, then by introducing capacitance within the system, we're going to take that positive reactive power and bring it down a little bit further, closer and closer towards that real axis. So the way that we actually do this is essentially a system in which we want to ensure that not only the voltage across the original resistive inductive load stays the same, but therefore that keeps that current that's actually going through that load the same as well. So we usually think of keeping the source, that actual source that's going to the load, we keep that parallel with it, because that ensures the voltage will stay the same, and also the current through that load actually stays the same. And so we actually kind of neglect, in a sense, that transmission impedance that's actually on that line. So in this case, guys, if we hook a capacitor in parallel to that resistive inductive load, then we actually keep consistent that voltage across the original resistive inductive load, therefore also keeping the current through it also the same. But by keeping basically that capacitor bank there in parallel, we actually essentially change the amount of apparent power that's actually being introduced in the system. So in this case, one way that we can actually calculate a capacitive value that we could hook up to the system is simply by taking the amount of reactive power that we actually want to lower the original reactive power by, simply dividing that by essentially what we would see as the angular frequency within the system. In this case, most of the time we're going to be working with 377 radians per second, and then multiply it by the squared value of the absolute value of the RMS voltage. So in this case, what we're going to be doing, guys, is taking that, most importantly, taking that original apparent power, and then we're going, by lowering it a certain amount of negative reactive power within the system, or what we call the corrected reactive power, then essentially what we do is that we create a new apparent power in the system, getting this closer and closer and closer down towards the real power. And as close as we get that, if you remember that the real power divided by the apparent power gives us the efficiency or the power factor within the system. So as we get closer and closer and closer by lowering that apparent power down, we decrease the phase angle between basically that real power and then also the reactive power. Or if we go back to theta V minus theta I, we're causing that phase angle for the voltage and the current to get closer and closer and closer and closer to where they're almost in phase. And as we have said before, resistors, their phase angle of the voltage and the current is exactly the same. And so if the power that we're delivering in our system has more of an efficiency or a power factor to where theta V minus theta I gets closer and closer to 0 degrees, then we're actually utilizing mostly power that we're actually going to be absorbing and burning up within basically resistive portions within the circuit. So let's take a look at an example of how we could actually calculate that capacitive value by finding an original complex power, looking at how we actually want to correct that reactive power, and then seeing and verifying that by introducing a parallel capacitance that we actually did in fact create more of an efficient system. So let's take a look at this guy here. We have 120 at 0 degrees RMS voltage with an angular frequency of 377 radians per second. And in parallel with that, we got 25 ohms as well as an inductive portion of the load of J15 ohms for that inductive impedance. So what we're actually going to do here, guys, is let's take a look at that load first. Look at that complex power from the load. And so VRMS squared over Z conjugate, that's 120 squared over 25 minus J15, and that comes up with 423.53 watts plus 254 var. So in this case, the total complex power is 423 plus J 254 volt amperes. So let's just say hypothetically, I don't know, it's Sunday and it's brunch time. So let's just go ahead and just correct that by 200 var. Sounds like a good number. Just go ahead and 200 var. Let's knock it down by that. So what we're going to do, guys, is we're going to take that original 254 and we're going to bring that down by 200 var. And when we take QC and we denote that 200 var will be the reactive power that we're going to correct by, and then divide that by VRMS squared, the absolute value, multiplied by 377 radians per second, we get a capacitive value essentially of 36.8 microfarads, or 36.8 times 10 to the negative 6. And so if we calculate our impedance of that value that we're going to introduce in parallel to that resistive inductive load, we get essentially negative J72 ohms for our capacitive impedance that we're going to be introducing into the system. Now, considering that we put this guy in parallel, we are not at all changing the voltage across that original load at all. And we're not changing the current through it by any means. But what we're going to do is affect the amount of apparent power in the system, that magnitude of our instantaneous power. And so what we're actually going to get here, guys, when we recalculate our new complex power that's actually being supplied by our source, then essentially what we get is we take the new impedance value of these two branches in parallel, and then we take 120 squared divided by 33.54 minus J4.28. And that actually gives us, essentially, guys, what we see as 423.5 plus J54. Oh, man, look at that. Look at that. Now we have 254, and the new reactive power actually becomes just 54 var. So essentially, we brought that 254 down by 200, down to 54. But notice something, the most important part here, that real power of 423 did not change. That did not change, therefore we're supplying the same amount of real power in the system, but with less reactive power on the line. And that's really good for not only the power company, but also for basically whatever company we're actually supplying power towards. So in this case, guys, essentially what we did was we took theta V minus theta I, we brought that a little bit closer together. And by doing that, we have increased the efficiency of our system. We'll see you next time.